again welcome to the NPTEL online certification course on CMOS digital VLSI design, and we will start the second module of logical effort. We have finished the first module and we saw what is the meaning of logical effort in the first module. We also understood why logical effort is important in calculating the delay between the primary input and output of a system. What we will be doing in this module is primarily looking into how to calculate logical effort, and then using logical effort how can we calculate the total delay, right. So, we had discussed what is logical effort in the previous module, and now we will be discussing how to calculate or evaluate the logical effort in this module. Now, let us look at how to calculate first of all the logical effort for any of the conventional gates available to you. Maybe it is a 2 input, 3 input, n input, a NAND gate, NOR gate, XOR gate, whatever gate, combinational logical block. Let us see how to do that. So, as I discussed with you, logical effort is primarily the ability of a particular gate to drive the same amount of output current as a minimum sized inverter, right. So, I have an inverter whose low to high and high to low delay has been made equal by making it 2:1. So, if you look at this slide here, in this slide you will see that this is basically made 2:1, which primarily means that it's in. So, therefore, if you look from input side, right, if you look from the input side, its C in, which is the input capacitance, is basically 2 plus 1 3. So, it is 2 plus 1 plus 1 3, because any input has to drive this PMOS as well as to drive this NMOS, right, and therefore, the input capacitance is basically 2 plus 1 3. So, I have my C in to be equals to 2 plus 1 3. So, what we get from here is that we define therefore, the logical effort of a simple inverter G to be equals to that. So, if it is 2 by 3 and if you have a simple inverter available with you, then we define the G of this to be equals to 1, which means that with respect to itself it will drive exactly the same amount of current in the output load, provided a 2:1 ratio is maintained between the PMOS and the NMOS. So, any inverter with a sizing of 2:1 between PMOS and NMOS will have its logical effort G equals to 1. That is the basic definition of a logical effort. So, calculation of logical effort for a basic CMOS, right, is straightforward and simple, and the value is equals to 1 provided the PMOS to NMOS ratio is 2:1. Let us have a look at maybe a 2 input NAND gate, which is available here, as you can see here, right. If you look here, the NAND gate has got 2 PMOSs in parallel in the pull up, right, which is this is, and this are 2 parallel pull up PMOSs, and we have got 2 series NMOSs in the pull down. So, this is my PDN, right, this is my PDN and this is my PUN, right, PUN. Now, why I am making this PUN 2 and 2 aspect, this 2 and 2 are basically the aspect ratio. I want to make it such that now the delay, high to low delay for a 2 input NAND gate is exactly equal to a high to low delay for a simple inverter, which is there in this slide. So, so therefore, TP high to low of a NAND to logic, right, is exactly equals to TP HL of an inverter, a skewed inverter, which is shown here. Why? Because when you have got W by ratio 2 and you are in series to each other, this effectively comes out to a fact that you have only one device with aspect ratio 1, right. I will explain to you what do I mean by that, which is basically, if you look carefully here, and I will just show to you what do I mean by that. So, if I have got, let us suppose 2 transistors which are 2 each, right, and they are in series to each other, then this is equivalent to saying that I have a single transistor of aspect ratio 1. I hope you understand this point. Why is it like that? Because see, this was W by L, so you have doubled the ratio here. So, the resistance offered by this transistor is R by 2. So, suppose this is R, then this is as R by 2, this is also R by 2. So, R by 2 plus R by 2 in series will give you R. So, this is what I wanted to tell you, that if there, for example, if you have a therefore a 3 input NAND gate, then you will have pull down which are 3 in number, then this each one will be R by 3 R by. So, if you make it 3 R 3 and 3 aspect ratio, then this will be R by 3 R by 3 R by 3, and if you add all these R by 3s together, you effectively get equals to R, which is nothing but the resistance of the pull down network of a minimum sized inverter, right. So, this is how we calculate the value of your logical effort, the pull down case, right. So, therefore, your aspect ratio is 2 and 2 here. Now, let us go to the pull up network. Pull up network is relatively easy, because please understand, in pull up network, for low to high propagation, either of the two has to be switched on, not all, both of them does not have to switch on, right. Either of the two and PMOSs have to switch on. So, when they switch on, their W by L ratio should be exactly equals to the PMOS W by L ratio of this one. For a low to high transition, exactly that of the inverter. So, therefore, an input which is being fed here, right, will actually see this PMOS and it will actually see this NMOS. So, this is 2 plus 2, therefore, your input capacitance is basically equals to 4, right. So, your input capacitance is basically equals to 4, and therefore, we define the G, the logical effort, to be equals to 4, which is this one, this plus this, divided by 3, because for an inverter it is 3. So, we define G to be equals to 4 by 3. I hope you have understood how we are calculating the value of the logical effort here. And the same concept, let me again explain to you by the concept of a NOR 2 logic. So, I have a NOR 2 logic, which is basically 2 input NOR gate. In a 2 input NOR gate, let me give you an idea. If it in a 2 input NOR gate, what I will get is something like this. 2 input NOR gate will look something like this, right, and you will have this, and then you will have in parallel this, right. So, you are driving with this, and then you have input here, and then you will have A input, and if this is B, then I will be driving here with B here, fine. So, I have got two inputs A and B. Now, I want to make it exactly equal to inverter 2:1, which I discussed with you just now, right. So, if you look, if you have a signal being fed here, it sees a C in to be equals to 3. Let us see what happens in this case. I want to make it equal. So, as my discussion was there for the previous case, I can also tell you that this will be therefore equals to 4 and 4. Why 4 and 4? Because if you make it 4 and 4, see, it was, if this was 2, if this is R, this will be R by 2, right, because it is double the width. So, I want to make it R by 2. So, each one, if it becomes R by 4, then R by 4, then if I add R by 4 plus R by 4, I get R by 2 as the effective value. So, therefore, this will be 4 and 4, whereas this can afford to be equals to 1. I suppose you have understood what I am trying to tell you is that why this is 4, and not 2. The 4 becomes R by 4, and therefore, R by 4, if you add up, we get exactly the same resistance as offered by the pull up PMOS transistor in an inverter. So, therefore, C in this case is nothing but 4. So, if I am inputting an input 0 to 1 transition in A, right, then it's this input sees a loading of 4 here and a loading of 1 here. So, your 5 is the loading which you see. So, 5 divided by that 2 plus 1 3. So, 5 by 3 is the logical effort for a NOR 2 logic. Is it okay? So, this is how you calculate the NOR 2 logic. Let me explain to you again maybe a NAND 3 logic. NAND 3 logic will have PMOS's 3 NAND gates in the up one, like this, and then you will have 3 PMOSs in series, NMOSs in series, and each will be connected to a external loading. So, I will have A, I will have B, I will have C. So, if you want to make it exactly equals to a if you want to make it exactly equal to a single sized inverter, which is something like this, right, 2:1 ratio, 2:1, and then you want to find out, then of course, as I discussed with you, this will be all 2, has to be all 2, right, because you require only one of the PMOSs to switch on for a low to high transition. So, this is my output here, this is the output here. So, I only want one of the PMOSs to switch on, and all the PMOSs switch on in order to ensure that you have a low to high transition in the output, whereas I want all my NMOSs to switch on to have a high to low transition. And please understand, each one therefore should have thrice the value available to it, because then this will be R by 3 plus R by 3 and this will be R by 3. So, R by 3 plus R by 3 plus R by 3 will give you R, which is nothing but the resistance offered by the NMOS in this case. So, a signal fed here will actually see 5 as the input, and therefore, it will be 5 by 3 again the logical effort for a 3 input NAND gate. So, therefore, you see, more complicated the gate is, or larger the number of input profile available to you, larger will be its logical effort, right, because it becomes more difficult for the whole gate structure to give the same amount of current as output current as your small sized inverter, right. So, this is what I wanted to just and this is how you calculate the logical effort for all the other gates, right, and this. So, I get 5 by 3, I get 4 by 3 for a 2 input NAND, I get 5 by 3 for a 3 input NAND, and I also get 5 by 3 for a 2 input NOR, right. So, these are the few things which you should be aware of, right, and this is what I was trying to say, that therefore, for an inverter it is 1, and if you, this is a logic gate. So, this column is basically your logic gate, these are the number of inputs which you see in front of you, right, and we will discuss this later on parasitic delay, but this is the. So, if you have obviously you can have 1 input NAND gate, NOR gate, XOR or multiplexer. So, you have 2 input, you have 3 input and n input. The general rule of thumb is that for a NAND gate it is n plus 2 by 3 is the value of your logical effort, and for a NOR gate it is 2n plus 1 divided by 3. Whereas, for a multiplexer the logical effort is exactly equals to 2 independent of the number of inputs, and for a XOR gate, which is basically a parity checker, I will have number of inputs. For 2 it is 4, for 3 it is 12, and so on and so forth, right. And so, this is how it looks like. What is parasitic delay, by the way? Parasitic delay, as I discussed with you, is primarily the delay which is happening by virtue of the capacitances and other things, parasitics within the circuitry. So, if you have an inverter, you will have, let us suppose inverter has got a parasitic capacitance of a parasitic delay of P inverter, then a NAND gate, n input NAND gate will have n times the P inverter, because all those n gates are putting into the output side, right. I suppose I am making it clear that for all your n input NAND gate or n input NOR gate, the output logic will be loaded n times. So, your parasitic delays will be therefore n times P inverter and n times P inverter here, right. If you are doing a multiplexer, it is 2 n times P inverter, because not only you will have both the arms, but you will also have the select lines coming into picture. So, these are the typical parasitic delays which you see in front of you in terms of logical effort and the understanding. We come to a FO4 delay, the calculation of a FO4 delay, which primarily means that I have a single inverter here, which is this one, and it is driving 4 such inverters in this case. So, that is the reason we refer to this as a fan out 4, FO4. FO4 primarily means that, fan out basically means that if a single sized inverter is driving similar inverter, right, then we define the number of inverters it is driving to be as the fan out. So, if you look very carefully, inverter number 1 is driving say A, B, C and D inverters from an external circuitry, and all are equally sized, and therefore, we define that this to be as a FO4 or fan out 4. Now, we have just now seen that f, small f, is basically G into H, where G is the logical effort, H is the electrical effort which you see. Now, logical effort for an inverter, as I discussed to you, is always equals to 1, which is 1. Now, why H equals to 4? H equals to 4 is very simple, that the reason being that if you look at the we are discussing about the delay by this example here. So, if you have a delay, so if you look at this point, which is the transition between the first and second case, then at this point it sees 4 equally sized inverter connected in parallel. So, if I assume this to be as a unity here, right, 1, then this will be exactly equals to 4, provided all the inverters A, B, C and D have equal loading. So, this will be 4. So, I get 4 into 1 as equals to F. So, 1 F will be equals to 1 into 4 and therefore F happens to be equals to 1. As I discussed in the previous slide, if you remember that for a simple inverter it is P inverter which you see. So, if you look very carefully for an inverter, this is P inverter which you see as the parasitic delay, right. So, if you look at the parasitic delay, I get P inverter equals to 1. So, the total delay therefore will be F plus P inverter. F is 4 plus 1 5. So, I get the delay unit of 5 delay units, right, I get 5 delay units, right, which means that the absolute delay will be nothing but D into tau, where tau is approximately 12 picosecond for a 180 nanometer technology. Now, this is fixed, this tau is by virtue of the fabrication technique which we are using. So, for a 0.18 micron technology, this tau is typically 12 picosecond, right. Now, by virtue of the circuit, you have actually seen a 5 time increase in the value of its basic value. So, what I do, I multiply 5, which is this one, multiplied by 12 and therefore, I get 60 picosecond as the absolute delay between input and output of a particular gate, right. So, this is how you calculate the fan out FO4 of a basic inverter delay or a basic inverter, right. And this is because this is driving 4, you get 4 as your H, right, electrical effort. Now, if you were driving 3, I would get H equals to 3 and so on and so forth, right. So, let us see what would have happened if H equals to 3. If H equals to 3, then I will get this to be equals to 3. So, I will get this equals to 4 and therefore, I will get this equals to 4 and I will get 48 picosecond. So, you see if one inverter drives equally sized inverters, if the fan out is larger and therefore, you can see the delay will be also larger as the fan out becomes larger and larger. And the reason is the load capacitance starts to become larger and larger, which reduces the delay drastically for a FO4 delay, right, and that is the reason why we get a larger and larger delay. Let us look at another example where we have a 4 input NOR gate, right, this is a 4 input NOR gate and it is driving 10 such 4 input NOR gates. So, this is driving 10 such 4 into NOR gate, this is the 10 NOR gates available to us, right. Now, F again is G into H, since H is basically the capacitance at this point with respect to the capacitance here, I get H to be equals to 10, right, because it is each inverter is driving 10 load, therefore, your H equals to electrical effort equals to 10. G is 9 by 3 for a 4 input NOR gate, you can find it out, or even in a simple form you can find out the value. Then if you multiply these two together and of course, P inverse equals to 4 for a 4 input NOR. If you add those two together, I get D equals to 34 and generally it is again as I discussed with you 12 picosecond for a 180 nanometer technology, you multiply 34 with 12, I get 408 picosecond, which means that the delay between input and output for a 4 input NOR logic gate is basically 408 picosecond, right. So, 1 upon that will give you the maximum frequency of operation of a 4 input NOR gate made with 180 nanometer technology. Therefore, even if you do not understand anything and you do not want to understand this part as such, you can actually see that if your fan out is large, which means that in rather than 10, if it is at 20, you automatically see that your delay becomes larger and larger. This is the first thing. The second thing is, if your gate is more complicated, for example, rather than using a, let us suppose a 4 input NOR, I would have used a 5 input NOR, right. If I would have used a 5 input NOR, then the G value would have been larger and therefore, my overall delay will also be larger, which means that more complicated a gate is in terms of either larger number of inputs or the gate becoming or the structure architecture becoming more complicated, the delay actually rises up because of that, right, and that is the reason we generally require to keep a lower value of delay by choosing a lower mode. So, many a times you must have heard that to realize the logic I can use 3 input NOR, right, but I can also use a 4 input NOR, it reduces the area, but the price you pay for it is exactly the same, that rather than using a say maybe 4 input NOR, it is advisable to use 8 2 input NOR to achieve the same result by doing certain manipulation using Boolean Boolean expressions, and the reason being that you actually have a logical effort which is much higher, and that results in a larger intrinsic delay of the effort. That is what is the reason why we get it. So, logical effort therefore ensures that the overall delay by balancing the delay among all the stages, which means that between two stages, if I am able to balance the delay, I will get the minimum delay overall across the path. But if I have therefore multiple devices across a path, then the path logical effort will be nothing but the multiplication of each logical effort of each gate. So, it is G1 multiplied by G2 multiplied by G3. So, in a path if there are say 3 transistors and then you have got something here, some and then the sum here, you multiply the logical effort of this with this and you get the total logical effort. Similarly, the path electrical effort H is nothing but C out by C in. C out is the output capacitance of the end of the path, and C in is the input capacitance of the primary input, which is this one, right. Now, branching effort is something like this, that if you have a signal coming here and it is getting branched, right, and this is your critical path, let us suppose, then we define this to be as the on path and this to be as the off path. Then we define branching effort B, small b, to be equals to C on path. C on path is the total capacitance on the on path plus C off path, total capacitance on the off path, divided by C on path, right, and this is how you define your branching effort small b. Similarly, if this branching is going on for a larger for a large values of branching is there, then the path branching effort will be nothing but the multiplication of all these branching efforts to a larger extent. So, we define a new term now, we define the term to be as F, which is basically known as a path effort, and it is equals to G multiplied by B multiplied by H. So, G is the total path effort, total logical effort, this is your electrical effort, and this is your branching effort. So, if you multiply all of this together, I get F, the total path effort, right, and if you multiply B into H, which is this one, I get summation HI this thing. Therefore, the path delay of the path will be nothing but summation of individual delays, which is nothing but df plus parasitic delay, which you see here. We have already discussed this to be is equal to gi hi plus pi. So, finally, what I get delay to be equals to is equals to gi hi plus summation of pi. Pi is the parasitic delay, this thing, right. Now, the path, I will just make a statement here that the path delay is the least when each stage in the path bears the same stage effort. So, if you have got single path and in the single path you have path delay, then if the path delay is least, right, if multiple paths have the same stage effort, right, and that is pretty important, which you see in front of you. So, for an n stage network, stage effort for each stage will be f gi into hi, which is nothing but f capital F to the power 1 by n, which you see here, right, and then that is what is the meaning of a stage effort as far as is concerned. The minimum achievable delay along a path will be, therefore, you need to just differentiate it and you get something like this, whereas the capacitance seen in the input is nothing but C total minus C I by hi, where hi is nothing but C out minus I total divided by C in input. So, C out I upon C in I is basically your hi bar, right, which you see in front of you. So, just to recapitulate, what we did today was basically give you that if you have number of stages equals to 1, we define path to be equals to n. If you in a stage ratio, logical effort is G, in a path it will be multiplication of G across the whole path. Electrical effort is C out by C in, right, and we define capital H for path to be equals to C out path upon C in path. Branching effort for a stage is C on path plus C off path divided by C on path, whereas branching effort for a whole path is nothing but multiplication of each branching effort. We define effort F equals to G into H, and for a path we define G into H for sure, capital G into capital H, but we also multiply that with the capital B. Capital B is the total branching effort between input and output. Effort delay is F, and if you sum the effort delay across the whole network, we get df. We have parasitic delay as P, and therefore, we will have summation of parasitic delay to be equal to the total path delay, and therefore, delay D equals to F plus P, which is nothing but df plus P, where df is nothing but summation Fi, right, summation Fi, and once you are able to find the effort delay, right, you will be able to find out the value of this thing. Parasitic delay is already known to you. So, this we have learned till now. We have also learned that therefore, we have also therefore learned now today by this module was how we calculated the value of logical effort, and therefore, given any gate, any input gate, you should be able to calculate the logical effort. From logical effort, given the load capacitances, you can calculate the path effort. Once path effort is known, you already know the parasitic value of a particular gate, and therefore, you can be able to calculate the total delay, which is equals to f plus p, and you can actually calculate the total delay available to you, right. This gives you a brief idea about how you are able to achieve a relatively a low value of path delay in this design, right. And this is the whole motivation for doing this chapter on delay. Fine. With these, I thank you for your patience hearing. Thank you.